we're going to do a little review of factoring today. And I'm not going to talk about why we factor. I'd like to. A lot of times I want to spend a little time up front talking about why it is we do this. But we have a short day today, and I really want to get to review it. So we'll get back to that. Well, I won't be here tomorrow, so that'll be on Wednesday. Okay, tomorrow we get a away game in Central Oregon. I want to get you to the point where you can really just you can start practicing factoring. So go ahead and flip to page 2 in the stapled handout. That's where we're going to start. The part where it says factoring refresher. Okay. And so this is all going to be a review of stuff that you did in Algebra 1. None of this will be new, but I think it's probably pretty important review. So first of all, let's just spend a second talking about what does it mean to factor something. Factoring is a word we throw around a lot in algebra classes, and you probably have an idea what a factoring problem might look like, but let's make sure you understand what that word really means. So let's go back to a non-algebra example, just using numbers. You're all familiar with this process. We do it all the time. 2 times 3 equals 6, right? We call that just multiplication. So this would be multiplying. Factoring is literally just the opposite of multiplying. It's when we're factoring something, we would start with the 6 and we'd write it as being equal to 2 times 3. So we're just undoing the multiplication process, right? So the whole point of factoring is we're going to take something and we're going to write it as a product of smaller factors. Okay? The same thing holds true for algebraic products. It doesn't have to be just numbers. It could be stuff with variables in there also. Like what if we did x plus 3 times x minus 5? Just quick review. How would I multiply that stuff out? Distribute, right? I'm hearing people say distribute, sure. So if I'm multiplying 2 binomials together like that, bi means 2, right? So I've got 2 factors that have 2 terms in each. I'm just going to distribute from one to the other, right? So we could distribute the first x to both terms in the second factor. And what would I get? So I'm going to get an x squared minus 5x. Good. And then I would just have to distribute the positive 3. And what's that going to give me? Plus 3x minus 15. Good. And would you agree that when I combine all the like terms, I'm just going to get this? Right? If I combine the x terms. Okay, so then once again, we'd say that this process of starting where we did and ending over here we call multiplying, or when we're doing it with variables, a lot of times in math we'll call it expanding. And I think the reason is just that notice that we ended up with both of these had 2 terms, while our answer has 3 terms. So we're expanding it out and making it bigger, having more terms. Okay? So whatever you want to call it, the important thing for today is that the reverse process is called factoring, and that's what we want to focus on. It's easier to multiply. The rules are simpler to follow than it is to factor. Right? So we want to practice factoring today. Okay, the first part of that is let's focus on the concept of a greatest common factor. Okay, so a greatest common factor is just the greatest number and or power of the variables that divides evenly into 2 or more expressions. So let's take an example. Once again, let's start with one maybe that doesn't even involve variables. Let's just start with one involving numbers. The very first thing, let's calculate what is the GCF. Let's pick 2 numbers. Let's do like, how about 15 and 35. What's the greatest common factor of 15 and 35? 5. How come? You're right. How come? Say it again. It's the biggest number that divides evenly into both of those, right? So the answer would be 5. Okay, there's a way of showing that that might be interesting for you to take a quick look at. Because what if they were really huge numbers? 15 and 35 we can deal with. They don't have very many factors, but what if they were numbers that were in the thousands or something, right? Then it would be hard to find the biggest number that divides into both. So one strategy is we could do a factoring tree of both. So what are the factors of 15? 3 and 5. What are the factors of 35? 5 and 7, right? And those are both prime. So then in this case, the only common factor is 5. What if we had some different numbers maybe that were a little bit tougher? Like what if we did something like 24 and 18, how about? Okay, what if we wanted to find the greatest common factor? New spot here. 24 and 18. What would that answer be? 6, okay? And we could show that if I did 24 and I made a factor tree. Remember, when I'm making a factor tree, there's no one right or wrong way to do it. Every time I have a branch, I just have to branch into two numbers that multiply to that, right? So what are two numbers that multiply to 24? 6 and 4, okay? So I could do 4 and 6. Now I'm not going to stop there though, am I? Because both 4 and 6 factor some more. What does 4 factor into? 2 and 2, and then 6 factors into 2 and 3. Okay, good. So now what about 18? 6 and 3, okay. 3 and 6, and then we already know that 6 factors into 2 and 3. So if I'm going to look for the common ones then, it looks like I've got a 2 there and a 2 there. And then I've got more 2's here, but no other 2's here. So I'm done with the 2's. What about the 3's? I've got a 3 there and a 3 there, and then no more 3's in my first factor tree, even though there are more in the second, right? So then what are the common factors? 2 and 3. Well, what's 2 times 3? 6, right? Make sense? So if we had really big numbers, we could always use that approach, okay? Well, now let's move down and let's look at some that involve variables also. So what about 12k and minus 18? So 12k minus 18. What's the biggest thing I could factor out there? Just be 6, wouldn't it? Okay, so my greatest common factor for this one is just 6. How come no k? How come I can't factor out a k? Doesn't have any k's, right? Okay, so then if I were to write this in factored form, there's two kinds of questions you're going to get on your first assignment. A couple of them are just going to ask, what is the greatest common factor? And the correct answer is 6. What if we want to write this in factored form, though? If I want to write this in factored form, what's this going to equal? Well, it's going to equal 6 is the greatest common factor, and what's left behind when I factor out a 6? Okay, good. And the way we could look at that, we could just ask ourselves, if I divide by 6, what are we going to get? If I divide the first term by 6, 12k divided by 6 is what? 2k. Okay, so then we're going to get a 2k there. And then what about 18 divided by 6? What's that going to give me? Okay, good. So I'm going to get minus 3. Does that make sense? Okay, so then factoring out a greatest common factor is just the opposite of distributing, isn't it? Because how would I check to see if I got this right? Wouldn't I just multiply the 6 through to see if that's what I get? Right? 6 times 2k gives me 12k. 6 times negative 3 gives me negative 18. Check, right? So when we're calculating a greatest common factor, that's really just undistributing. Very same thing, right? I'm going to write that down. That's such an important thing. Seems like a minor thing, but it's an easy way to think about it. So factoring out the GCF is the same as undistributed, right? Okay, what about the next one? This looks harder. So what's my GCF gonna be here? I've got a number part, right? What's the biggest number that goes into 40 and 64? 8. Okay, so I got the number part. Now, what about the x's? Well, yeah, what's the biggest power of x that's going to divide into x to the 4th and x to the 8th? X to the 4th. It's always going to be the smaller of the two, isn't it? Right? So we're going to get 8 x to the 4th. And then what about the y's? Just y. They each have a y. So I could divide y into each of those terms evenly, right? So there's my greatest common factor. Let's see what happens when I want to, so there's one answer that we might get. Now, what if the question was, write this in factored form? So I'm going to have my greatest common factor, 8 x to the 4th y, and then what's going to be left over? So we could find out if I divide the first term through by 8 x to the 4th y, what do you notice? The y's cancel, right? And 40 divided by 8 is 5. Okay, so we know we're going to get 5. And then x to the 8th divided by x to the 4th. How do we divide like bases like that? X to the 8th divided by x to the 4th is what? How come? Because you subtract, right? When you divide like bases, you subtract exponents. So I get x to the 8th minus 4. And then look, the y's just canceled, didn't they? Right? So there's my first term. And I'm going to put a circle, a yellow circle around the plus sign so we can keep track of where each of these comes from. And then what about the other part? If we divide 64x to the 4th y by 8x to the 4th y, the variables all cancel, don't they? X to the 4th over x to the 4th cancels. Y over y cancels to 1. And what's 64 divided by 8? Yeah. Okay. So there it would be in factored form. I undistributed my 8x to the 4th y. Okay, does that make sense? Okay. Phones should all be away, please. Why don't you put it like in your pockets away so they're just totally out of the way. No temptation there. Okay? One more. Well, actually, a couple more. How about this one? Everybody, take a look at this for a second. Try this on your scratch paper. So, Joseph, what's going to be the biggest number that divides into all those? 7. Good. Okay, Ellen, what's the biggest power of m that I could undistribute? What do you think, Dominic? Not 1. What's it going to be? Yeah, it's going to be m squared, isn't it? Right, because that's, all of this has m to the 6th, that has m cubed. They both have extra m's to give away, but this one only has an m squared to give away, right, that I can divide away or undistribute. So it's always going to be the greatest common factor. When it comes to the variable parts, the greatest common factor of the variables is always going to be the least common power, the smallest of the common powers, right? Does that make sense? So of the m's, it would be an m squared. Okay? And if I divide that out, what am I left with? So if I wanted to write this in factored form, I'm going to get my 7m squared, and what's going to be left behind? What am I going to get? So what is 14m to the 6th divided by 7m squared? What do you think? Molly, what's that going to give me? 14m to the 6th. If I undistribute a 7m squared, what am I going to be left with? And I'm just dividing, right? I'm just going to divide that by 7m squared because I'm undistributed. 14 over 7 is 2. And what's my power of m going to be left over? To the 4th, because that, right, m to the 6th divided by m squared would be m to the 6 minus 2. Okay? Mackenzie, what's going to be the next one? If I divide negative 35m cubed by 7m squared, what am I going to get? There you go, negative 5. Add to the 1, right? Yeah, so just leave it as negative 5m. Okay? And then the last one, negative 7m squared divided by 7m squared. Negative 1. Yeah. Okay. All right. Okay. One more of these. Guaranteed everyone's going to have a question about this one. Doesn't look so bad, but you're all going to have questions about it. Yeah, what's the question going to be? Is it negative or not? That's the question, right? Is the greatest common factor negative or not? Here's the rule. The answer is it is, and here's why. The greatest common factor inherits the sign of the leading term. Now, what in the world is the leading term? The leading term is just going to be the term with the biggest power of the variable. That's the one that dominates the function, right? So if we look at this guy, this guy right here, which is the leading term? Well, here I've got an x to the 4th, there I've got an x squared. X to the 4th is a bigger power of x, so that's the dominant term, that's the leading term. So because that's the leading term, we know that the greatest common factor is going to be negative. Okay? Yeah. Okay, so in this case, the greatest common factor is going to be negative, and what's the number going to be? 4. And what's the biggest power of x I can undistribute? X squared. There you go. Okay, good. All right, so we can skip that. So next issue then. So we know how to, we got a little practice with undistributed, finding greatest common factors. Okay, the next issue is factoring trinomials. Okay, factoring simple quadratic trinomials. So those are trinomials that fit the form ax squared plus bx plus c, where a is equal to 1. If a is equal to 1, the a goes away, right? And we just get x squared plus bx plus c. That's why they're simple, because a is equal to 1. Then it's a simple pattern, right? Now let's think what has to happen here. If I'm going to break this up into a product of factors, what has to go there and there? It's got to be x, doesn't it? Because when I distribute, that's the only way when I distribute to multiply this out, I'm going to get an x squared, right? So I know I've got to have an x and an x, but the tricky part, the part we need to review, is what about the magic numbers? What about the numbers? What do they have to do? Good, they always have to multiply to c and add to b. So in this case, they'll be multiplying to 45 and adding to 14, right? Okay. So let's start off by always playing the sign game when we're trying to find our magic numbers. If they're multiplying to a positive, what's that tell you about the signs? If they're multiplying to a positive, what's the only way the two numbers could multiply to a positive? What's one way? The two numbers could multiply to a positive. If they're both positive. What's another way? They're both negative, so they have to be the same sign. But if they're adding to a positive, they're both positive, right? So we know that those are going to be plus signs. And then what are the numbers that do the trick? That multiply to 45 and add to 14? 9 and 5. And we got it. It's factored. Okay. How could we check? Multiply it out, distribute, and see if we get that, right? Okay, next one. Notice that because a is 1, this is a simple kind, right? We know that what has to go there and there? Well, x, but in this case it's not an x, it's a w. Same thing though, right? And then what do my magic numbers have to multiply to this time? Again, multiply to what? No. Oh, you're thinking of what the numbers are. Yeah, I wanna know, what do they have to multiply to? 26. Okay, so for number 6, they're gonna have to multiply to 26 and add to what? To negative 15. So what are the signs gonna be? If they multiply to a positive and add to a negative, they're both negative, and what numbers would we get? Okay, 13 and 2, good. Done. Okay, last one. What about this guy down here? So we know it's gonna factor, or if it factors, I'm gonna have to have n's there because I have an n squared for my first term. What do the magic numbers have to multiply to? 1 and add to, okay, so they're multiplying to a positive and adding to a negative, so they must both be negative. And what numbers multiply to 1 and add to 2? 1 and 1. Okay, so there it is. That's good, but that's not totally correct. It's not simplified. Ah, good. When I multiply something by itself, it just means it's being squared, right? Okay, good. All right, so now let's move up in difficulty. These were simple because A was equal to 1. What about this one? Yikes. Where A is not equal to 1. Do you guys remember doing these kind? If you had Mr. Haygood, you probably called this slip and slide, right? Okay, well, we'll review that. We'll review that. You might have called it bottoms up. You might have seen it as bottoms up also. Okay, it could be either one. Yes, sir. Yeah. Okay, but it looks like we're going to have to use it. Or are we? What could I do? Ah, okay. Now, by dividing by 2, what you really mean there, if I want to write this, the instructions for this would be factor. Okay, so let me write that down. So number 11, what we're trying to do is factor. What that really means is we're supposed to write it in factored form. So we're going to write it as a product of factors. So when we're done with our answer, if I should be able to multiply it all together again and get this back where we started from. Okay? So John, when you say divide by 2, that's not actually what you mean. What you really mean is undistributed 2, right? Because the 2 has to stay there. It's got to still be part of our answer, right? So in other words, if we undistribute a 2, that's really just our greatest common factor, isn't it? The biggest thing that divides into all the terms. So the first step would be we could undistribute a 2, and then what's left behind? Okay, so yeah, I'm just going to divide each term by 2, aren't I? So Ellen, help me out here. So if I'm dividing each of these terms by my greatest common factor, I've just got to figure out what's going to be left behind. So what's 2k squared divided by 2? 2k squared divided by 2. Well, 1k squared, right? The 2's would cancel, and I would just get k squared. What's 16k divided by 2? 8k. Good, and it'd be negative, wouldn't it? Negative 8k, and then finally negative 40 over 2 would be. Okay, now look what happened there. That was something really good, right? When we factored the 2 out, the trinomial that we're left with is not a hard kind, it's a simple kind. Because inside these black parentheses, the coefficient of k squared, or x squared, or whatever our variable is 1. So we get to go back and use the simple technique where I'm just finding simple magic numbers, right? So what's the moral of the story there? Well, the moral of the story is always look for a greatest common factor whenever you're factoring something. It always makes life easier if you can find a GCF every time when you're factoring. So we always want to try that. Okay, so now let's finish this up. So we broke it up, we factored out the 2. What about the orange trinomial? What do my magic numbers have to multiply to if they exist? Kaylee, what do they have to multiply to? Say it again? Negative 20, good. And they're going to add to what? Negative 8, okay. So let's play our little sign game then. Right, we've got our 2 out front. And then if we factor this into pieces, well, what has to go there and there? K, good. So let's play our sign game. If two numbers multiply to a negative, what does that tell you about the signs? Jaylene, what's that tell you about the signs? If two numbers multiply to a negative, what's that tell you? So if two numbers multiply together and give you a negative result, what's that tell you about the signs of the two numbers? Okay, good, they're opposite. One's negative and one's positive. Gabe, if they add to a negative, which one must have been the bigger of the two? The negative must have been the bigger, right? Because when we added them up, we still got a negative result. So the negative one must have been bigger than the positive one, right? So here's what I recommend you do then. Let's always put the bigger first and the smaller second. And then I have to just think of the numbers that fit the bill. What numbers are going to multiply to negative 20 and add to negative 8? There you go, negative 10 and positive 2. And now we're done, right? We got it all the way factored. But what made that way easier? Pulling that 2 out front, right? Undistributing that 2. Okay, good. So we always want to try that. Okay, what about this one? If I want to write this in factored form, what would the magic numbers have to multiply to? And add to? Do they exist? No, that one can't be factored, right? That's not one that can conveniently be factored. And so really, we're factoring to solve quadratic equations, is what we'll talk about tomorrow. Well, we'll start that on Wednesday. So all we would do then is we would move on to another technique. Factoring wouldn't help us here with a problem like that. And we're not going to practice those so much because it doesn't work. We'll practice the ones where it does work. But just know that factoring as a technique for solving equations doesn't always work. When it does work, it's easy. But when it doesn't work, we have to move on to something else. Okay. So now, finally, what about situations like this? What if we've got a situation where A is greater than 1, so it's not equal to 1, and this time, is there a greatest common factor that I can undistribute? There is not. There's no number that divides into 2, negative 15, and 18, other than 1, right? That doesn't help us. Okay? So now we got to go to plan B. Or not plan B, now we got to go to the slip and slide technique. Okay, so what happens in these situations? So fill in the blanks here. This is the loose sheet right here, right? Everybody get that? Okay, so when you've got a situation where A can't be factored out as the greatest common factor, then here's what you always do. You're going to slip the A to the end of the trinomial and multiply by C. So let's take an example. Like let's take this example right here. And we'll just go through this step by step as we follow the steps. Okay, so we end up then with step 1. This is going to become x squared minus 15x plus, what's 2 times 18? 36. Okay? Step 2. Step 2 says factor this basic trinomial. So step 2, what's that going to break up into? I know I'm going to get x's there. What do my magic numbers have to multiply to? Okay, so we got to multiply to 36 and add to what? Okay, what magic numbers do the trick? Okay, and they'd both be negative, right? Everybody agree? So I'm going to get negative 12 and negative 3. Step 3 is we're going to divide both of your factors by the slipped value, by my original A. Well, what was the value that I slipped? A was a 2, right? Okay? So step 3, I'm dividing my magic numbers by A, and then finally, step 4, we're gonna reduce the fractions if possible, and then if any fractions remain, we're gonna slide the denominator up in front of the x, right? So then step 4, 12 over 2 reduces to what? 6, so I get x minus 6, right, that just becomes 6 over 1. Does 3 over 2 reduce? It doesn't. So then over here, I'm gonna slip that 2 up front, and it becomes a 2x minus 3. And we're done. Okay? That's the way you learned it from Mr. Higwood, right?
Yeah.
Okay? Is that ringing a bell? Okay, so let's try another one of those. Let's pick. Okay, I don't want to do that. I'm just gonna make one up. Actually, we'll just pick one off of there. What am I doing? Okay, so let's try. Let's try number 1. How about? So what's step 1? Okay, so we're going to slip the a times the c, right? So we're going to get x squared plus 5x plus what? 6, okay? Step 2. Factor. So what are my magic numbers going to be? 2 and 3. Everybody agree? Positive 2 and positive 3. Okay. Step 3. Divide each of those by 2. Oops. Right, 2, because that's my original a. Okay. And then finally, step 4. What's this one become? Okay. And how about this one? That doesn't reduce, so I slip the denominator up in front. Okay? Another one. Let's try another one here. Oh, 1 minute? Okay, never mind. We'll pause it there.